Welcome everyone to this webinar. My name is Tang. I'm a solutions architect at Rackspace Asia, and the focus of this webinar today is going to be around Hadoop. More specifically, we're going to introduce you to Hadoop as a tool for big data. Now, in this webinar, we aim to provide a high-level introduction of Hadoop, its ecosystem, its key components, followed up with a quick demo of Hadoop in action. Now, we're not going to delve too much into the motivations behind big data or Hadoop, but if you are interested in this, we will provide you some links to some previous webinars, as well as some information at the end of this webinar as well. Now, as a side note, in the coming weeks, we will also extend on this webinar with other webinars. We will delve deeper into the components of Hadoop. We'll teach you how to use them. We'll also teach you how to architect a Hadoop environment as well. So please do stay tuned for those upcoming webinars in the weeks and months. So to start this webinar, we're going to start with a very basic demo. The goal of this demo is to show you the very traditional approach to analytics as it stands today. And that is to take a single powerful machine that we use to crunch data on it. Now, our machine today is going to be a 32 CPU machine with 60 GB RAM, and it's also backed by SSD disks. And in this demo, I'm going to do something very simple, and that is to count the number of times the word Hadoop occurs in a very large data set, and that data set is going to be Wikipedia. Now, I've downloaded the entire Wikipedia from the link on the slide, and let me switch over to show you it now. Okay, so if I were to show you the data set, there it is here. And as you can see, it's a 48 gig XML file. If I were to hit out the first 100 lines of it, you can see that it's got some very Wikipedia-like data within it. Now, I'm going to use a very simple program, a simple Java program, to actually do the counting. And as you can see, this is my Java program here, and if I cast this out, you can see that it is very simple. The algorithm is not particularly long or complex. I simply take a line, I use a regular expression to count the number of occurrences of the word Hadoop, and then I take that count and add it to a master counter. And that will overall count the number of times that Hadoop occurs within Wikipedia. So I'm going to initiate this program now. Okay, and I'm going to time the amount of time it takes to run. Let me initiate that again. Okay, and we're going to leave this running in the background, and we're going to revisit the second half of this webinar. So what is Hadoop? Hadoop is not a single tool or package, but it's an ecosystem of tools that has become synonymous with big data. I emphasize that it's become synonymous with big data, but it's not big data. It's merely one of many tools that enables you to run big data jobs. Now, to give you a concise definition of Hadoop, it's a software framework that enables organizations to analyze huge quantities of data to gain useful and specific insights from that data by way of distributed computing. Now, it's important for me at this stage to define what distributed computing is. Now, distributed computing is simply a group of computers that interact together to achieve a common goal. When considering a computational problem, though, distributed computing refers to splitting a larger problem into smaller problems and having those smaller computers individually solve those problems, a very much divide and conquer approach. The advantage of this, of course, is that we can achieve massive parallelism, and that allows us to either solve the problem faster and more efficiently, or it allows us to process more data or more complex problems in the exact same amount of time. But distributed computing has traditionally been extremely challenging and expensive to do. When running a distributed computing environment, for example, there's a need to think about a number of different things like coordination scheduling, what happens if components fail, as well as service synchronization and so on. And that's all in addition to building the actual distributed program that holds the business logic. Now, this has led to a lot of people needing to invest a lot of money into people and talent, as well as components such as high-speed networking and central storage devices, something akin to a supercomputer, in order to achieve a distributed computing environment. And this is the direct reason why Hadoop is so popular for big data analytics. Hadoop makes it relatively easy to get started with distributed computing. This is because, firstly, Hadoop is an open source project and it is designed to run on commodity hardware, so from a cost perspective, Hadoop has a relatively small upfront commitment. But more importantly though, Hadoop provides an out-of-the-box distributed computing environment that has already been optimized for data analytics, that is reliable, that is scalable, and that is standardized. So that means organizations using Hadoop can focus on writing the business logic and the distributed program instead of worrying about the complexities or the wider complexities associated with distributed computing. Now, one piece I do want to highlight, and this is very important for Hadoop, is the concept of data locality. Data locality is fundamental to Hadoop's distributed computing approach, so it's important to understand it. Now, traditionally, distributed computing systems usually bring the data to the compute via high-speed networks that can make things very, very expensive. On the other hand, though, Hadoop works on the tenet of data locality, where it perceives things to be cheaper to move the processing to the data as opposed to vice versa. So what you'll find is that in any Hadoop environment, the processing of the data is done on the node where the data already resides. And very rarely does the data move around, or the raw data move around. Now, I mentioned a couple of slides back that Hadoop is an ecosystem of software tools and not a single tool. Now, shown on this slide is some of the tools that are within the Hadoop ecosystem. Of these tools, there are core modules that exist in every Hadoop environment, and there's also additional tools that provide additional features that make a data scientist's life or an administrator's life a lot easier, but they aren't necessarily critical to the Hadoop environment. Now, the core modules will be the focus of the rest of this webinar. In particular, we'll discuss in more detail two particular modules. Now, the four core modules that make up Hadoop are firstly the common Hadoop libraries, which aren't shown here, but as with any software package, they form the foundation. Next, you have the HDFS file system, followed by the Yarn resource manager, and lastly, the processing engine. Now, the first of the two core modules we'll discuss in more depth is HDFS. HDFS, or Hadoop File System, is a file system optimized for storing vast amounts of data for big data analytics. As mentioned previously, Hadoop provides all the components necessary for an out-of-the-box distributed computing environment that is already optimized for data analytics. And HDFS specifically is a component of Hadoop that defines how data is stored within a distributed environment. Now, there are a number of attributes that make HDFS optimized for big data. Firstly, as you'd expect, HDFS is distributed, meaning the file system is spread across a number of nodes in the cluster as shown in the diagram. The file system itself actually exists as an abstraction on top of a typical file system like NTFS or ext4 in order to achieve this distribution. When data needs to be stored in HDFS, the process is as follows. HDFS breaks down the data set into smaller pieces known as blocks. It then distributes those blocks to different nodes in the cluster based on resources that are available on those nodes, and the metadata service keeps track of the location of these blocks. Now, each node in the cluster will typically only hold a piece of a data set, but not the entire data set itself. The next thing that makes HDFS ideal for big data storage is that it's designed to be hugely scalable. And it achieves this scalability by taking advantage of the fact that it's distributed. Big data problems can typically measure in the petabytes of data, meaning that huge amounts of underlying storage is required. HDFS is designed to use commodity hardware and can be grown by simply adding new nodes in order to grow the storage linearly. And it's not uncommon for an HDFS cluster to consist of thousands of servers that each form an underlying part of the HDFS storage. Also, HDFS is optimized specifically for large files as well as reads. These are optimal traits for big data analytics, since big data problems often work with large files and really, if ever, write to disk. This also means that HDFS is not necessarily optimized for use cases outside of big data analytics, and therefore should be used carefully when taken outside the bounds of big data problems. And finally, HDFS is designed to ensure it keeps data durably. One of the major problems of administering a big data environment is backups. Any good administrator knows the importance of backups, but given the amount of data that we deal with in big data problems, it's often very, very difficult to use a traditional approach to backups. HDFS's approach to data protection, however, uses the concept of replicas instead of the traditional backups. When data is stored on HDFS, it is automatically re-replicated to other nodes, making redundant copies. If a data node is lost, we can retrieve it from one of those redundant copies. Now, by default, HDFS uses a replication factor of 3, so that means there will always be 3 copies of data in the Hadoop environment, as you can see in the diagram. If a node does fail, HDFS will self-heal and it will re-replicate the data to maintain its redundancy. A positive side effect of this, of course, is that we don't need to use typical data protection mechanisms like RAID that actually helps us reduce those costs even further. Now, these aspects of HDFS that make it ideal for big data problems. And as a result of this, HDFS is starting to become the de facto standard for big data analytics in a distributed environment, irrespective of the analytic system you use. Now, having described HDFS, the next core component we'll go into is YARN. YARN stands for Yet Another Resource Negotiator, and just as HDFS is responsible for defining how data is stored in a distributed cluster, YARN is the component responsible for scheduling, coordinating, and tracking the jobs across the distributed cluster. Now, this means that when a user submits a job to Hadoop, YARN's role is to split the user job into smaller subtasks, and then determine which cluster nodes those subtasks should run on. In the process of choosing nodes, YARN will account for things like data locality, as well as resource availability, in order to select the best node possible. As a job scheduler, YARN's responsibility also extends to tracking jobs to ensure they run reliably. If, for example, a subtask fails due to a node completely failing, then YARN is responsible for detecting that failure and ensuring the job is rescheduled onto another node. Without doing this, of course, the entire job will fail, which could have a major impact, especially if jobs can take days to run. Now, finally, YARN is a generic resource scheduler, meaning it's designed to run with many processing engines. I mentioned in the previous slide that along with YARN and HDFS, there is another core Hadoop module known as the processing engine. Now, the concise definition of a processing engine is a framework designed to run applications of a specific programming model. A data scientist will write an application based on a specific programming model. They would then feed that application to the appropriate processing engine, and the processing engine will then enact the instructions of the application on the data. Now, I'm not going to spend too much time talking about processing engines in this webinar, as I do plan to dedicate future webinars to the various processing engines that exist. But I will give you a little bit of context, and I'll let you know of probably the most well-known processing engine for Hadoop, which is Mapreduce. Mapreduce is a pretty basic programming model. It consists of 2 user-defined operations known as a map and a reduce operation. This map operation is run on data across a number of different nodes and is then recombined and filtered using a reduce operation to make it more easily consumed by the user. Other processing engines include Spark, which relies on a programming model known as resilient distributed data set, as well as Tiz, which is a variation of direct acyclic graph. Now, Yarn is designed to be generic enough to run any processing engine, provided it's properly implemented for Yarn. That means that if I do have a Mapreduce application, I can use the Mapreduce processing engine to execute the program. Following that on the exact same cluster, I can run a Spark application using the Spark processing engine. The advantage of this, of course, is that it gives Hadoop maximum flexibility, allowing us to run the best processing engine appropriate for a given use case, while still maintaining the same underlying infrastructure. Now, having described these core components, I do want to talk a little bit more about the Hadoop ecosystem. As mentioned previously, the Hadoop ecosystem consists of numerous software components. Additionally, however, the Hadoop ecosystem consists of numerous distributions. In a similar fashion to Linux, different distributions from different vendors aim to provide further functionality on top of the basic open source Hadoop. And often, this functionality can be proprietary. So, IBM and EMC, for example, each provide a distribution which comes with a proprietary software component that you can use standard SQL to query data. Now, probably the most common distributions at the moment come from Cloudera and Hortonworks, but deciding which distribution to go with really depends on the needs of your organization from a functionality, a support, and a cost standpoint. And there are numerous options that offer advantages over others in all these aspects. Now, another piece I want to touch on is the different Hadoop versions. At present, there are two versions of Hadoop. Version 1 introduced in 2008, and version 2, which was more recently introduced in 2013. Now, looking at the slide, the major differences between the two versions, aside from the standard functionality improvements and bug fixes, is that version 2 introduced Yarn. Prior to version 2, this job scheduling and monitoring was solely performed by the Mapreduce processing engine, and the community found this to be quite limiting. Now, although most people are moving to version 2, both version 1 and version 2 are still being supported by the community, as many organizations still utilize version 1 within their environment. Now, in this presentation, I've talked a lot about Hadoop. Hadoop is extremely important to the world of big data. So as we close out these slides, I feel it's extremely important to reiterate that Hadoop is merely a tool that enables big data. In other words, just having Hadoop does not mean you'll gain the benefits of big data. Data science and the data scientists that write the applications still need to be included to make big data happen. So when considering Hadoop and Hadoop projects, we need to be sure that we always consider that the data science must also always accompany Hadoop in order to get real big data value. Now at this stage, I want to move on to a quick demo of Hadoop. More specifically, I want to run the same test as we did in the first demo, but using Hadoop Mapreduce instead. We'll run this on a 10-node cluster that is running off Cloud Big Data and Rackspace Cloud. And by running this test, I want to show you the advantage of parallelism for distributed computing with Hadoop, where you'll see how much faster it takes to run the same test compared to in our first demo. So going back to demo 1, you can see that it's actually still running. Now, in previous tests, I found that it takes about 20 to 25 minutes, and it actually finds 245 occurrences of the word Hadoop. Now, let's switch over to our Mapreduce application. Just going to load up the Wikipedia file, so you can see that I have the same Wikipedia file. So as you can see, I've got the same Wikipedia file, and it's approximately in fact the same size as in demo 1, which is 47.4 gig. Now I've also got a a Mapreduce program that I've written, which is shown here. The actual program is Java, which is the demo main.jar. And this demo main.jar really consists of 3 files within it: a driver class, the demo main.java, a map class, which is the method demo, and a reducer class, which is the reduced file. Now, I'm not going to go into too much detail around this program, as I do plan to discuss this particular program in a later webinar, but the Mapreduce program, like in Demo 1, is Java-based and uses the exact same algorithm to count the occurrences of Hadoop. So let me execute this Mapreduce program. At this stage, I'm specifying that I need to submit a job to Yarn. I'm going to specify the jar file as well as the program to run. I'll specify the location of the file I want to process. And lastly, I need to specify where to put the output. So this is submitting the job to Yarn at this point. At this stage, Yarn is actually going to find out information about where the data is stored in HDFS. It's going to determine things like the resources available in the different nodes. And then it's finally going to actually initiate the job from a selected node. Now, it's actually started the map job at the moment. It's counting up, and this is what it looks like to actually perform a Mapreduce job. It'll simply count up from the map side, tell you how far it's gotten based on the percentage, and then following the map, it will then start to reduce phase. So we'll give that a little bit of time to actually perform that map job. Okay, and it should start the reduce job very shortly. You'll see the reduce grow, and the complete job finishes. The reduce task was pretty simple, so it ran pretty quickly. Now, as you can see, it actually finished the entire job in about 1 minute, and I'll check out the output to show you that it found the exact about 245 occurrences. Okay, and as you can see here, it did find 245 occurrences in the entire Wikipedia of Hadoop. So this took about 1 minute to run, and this job basically ran or read the entire Wikipedia, all 48 gigabits, and calculated the exact same value as I did in Demo 1. Now that's about 20 to 30 times faster than running on a single node, and that really emphasizes how important, how beneficial distributed computing can be from parallelism. And this means that we can process more data than we have been able to do before, as well as process faster as well. So this brings the presentation to a close. I do want to thank you for attending, and I do hope this webinar has been informative for you. I would like to remind you that we will have another webinar coming up in the coming weeks, which will focus more on HDFS, how to architect for it, and how to administer it. So again, I would like to thank you for your time, and if you do have any questions, please type it into the chat field, and we'll endeavor to answer those questions for you. Thank you.